Good morning, everyone. It's really an honor to be batting leadoff for a conference like this. And I'd like to start by just thanking the organizers for putting this together. I mean, it's been a yeoman's effort to, the amount of work they've done in the last couple of months to really bring this home and make it happen is amazing. So congratulations to you. It's going to be an interesting few days. It's going to be fun for everyone, I think. And although it's the Montreal Space Symposium, I think what we'll be seeing is talks from people from around the country, really getting a big picture of what's going on in this country. And it's appropriate that we're getting talks from around the country. As there we go. Whoa, that's flying, isn't it? Talk for me. Canada's involved in a number of ways in space exploration, whether it's supporting human space flight, to the International Space Station and potentially beyond, to visiting our closest planetary neighbors in the solar system, to looking out deeper into the cosmos and really trying to unravel the mysteries of the universe. Canada is involved in so many ways, whether it's in academic, through students, through industry. And really, the space program, the exploration program in Canada is tremendously exciting, trying to unravel the mysteries of the universe and really trying to understand our place within it. So what I'd like to do today is break off a small chunk of that, which is planetary exploration in particular, and just give you a sense of where Canada's been, where we are now, and a little bit about where we're going next. So in terms of planetary exploration, you can really think about this as facing two major challenges. The first is planetary science, so classic, trying to understand the formation and the evolution of planets themselves. So whether it's the interiors, their surfaces, their atmospheres, ultimately, by understanding other planets in our neighborhood, in the solar system, it can give us some insight into how our own planet formed and how it evolved. So these are really big pictures that we're trying to address across the entire solar system, but really bring it back to applications on Earth. Now secondly is astrobiology. This is the big one. Trying to address questions such as whether or not we're alone in the universe in terms of life is just such a fundamental question that we're trying to answer. And really it's fascinating, it's exciting to be part of this. And so we're starting to get to the point now where we're seeing indicators of habitable environments elsewhere in the solar system. And so we're really now at the cusp of being able to ask the questions about whether or not life ever evolved elsewhere in the solar system. Now, given that Canada is a rather modest space program, it's obviously not as large as NASA or ESA, we have to be somewhat strategic about the targets and the missions that we participate in. We just flat out can't be on every mission to every planetary body in the solar system. And so traditionally, Canada's interests have been narrowed around three targets of interest. Firstly, Mars, the Moon, and small bodies like asteroids. And so what this has allowed us to do is really focus our efforts and consolidate our expertise to make sure that we're maximizing the impact of our industrial research and our industrial capabilities and our academic research. Now, going back a few years, really the first exercise that we had as a successful planetary instrument was aboard the Phoenix Mars lander. Now, this was a mission that landed in the northern plains of Mars that was there to search for signs of subsurface ice and also to study the environment of the northern plains of Mars. Now, if you'll see this green laser pointing up, this is obviously an artist's rendition, but that was Canada's primary contribution to the mission, which is an atmospheric LiDAR, a laser system meant to measure atmospheric particles and composition. Which I'll tell you about more in the slide comes. So as I said, this was our first successful planetary instrument. This was a mission that launched in 2007. So the entire contribution from Canada was the atmospheric LiDAR and also a pressure and temperature system. So basically what this was a meteorological package that helped to understand and characterize the Martian environment in the northern plains. Now what we found particularly fitting was that this is the first time that snow had ever been directly detected on Mars. We found it was only appropriate that the people that should find snow on Mars would be Canadians. Moving forward then, building upon some of the expertise we gained, building an instrument for Mars is hard, trust me. And so that we took a lot of the steps learning with the Phoenix LiDAR, but applied some of this expertise in the next mission, which is the Mars Science Laboratory. So right now we have something called the Alpha Particle X-ray Spectrometer, or APXS, at the end of the arm of the Curiosity rover. Now, it's a long acronym, but you can really think of it as almost a radioactive soda can. Essentially what it does, it's got a curium source inside of it, and when you place it on top of a rock, it emits alpha particles. And these alpha particles excite the atoms inside the rocks, and the rocks end up emitting X-rays. And by measuring those X-rays, you can actually tell exactly what the rock is made of. So you're doing chemical composition through a combination of particle-induced X-ray emission and X-ray fluorescence. So really, basically, you can almost think of this as the nose of the Curiosity rover that goes and sniffs the rocks to understand what the composition is. Again, this can measure the elemental abundance of elements from sodium up to bromine. And this is now outdated, actually. We've gone just recently over 2,500 hours of operation. So it's a fantastic feat of engineering and science. We've been there for over 5 years now, measuring rocks, and we've been key to determining that various points in Gale Crater on Mars used to be habitable. So it's a fantastically successful mission, currently an extended mission 2, and we're hoping to keep this going as long as we can. Okay, so in terms of other missions that Canada's on, we've contributed scientific instruments, but we've also contributed hardware elements to various missions as well. So if you look at the ExoMars program run by the European Space Agency, it consists of an orbiter, which launched last year, and a rover element that's launching in 2020. What's particularly interesting is that through our partnership with ESA, Canada was able to contribute various subsystems to both of these spacecraft. So on the trace gas orbiter, we have a communication system that was built by MDA. And MDA also built the chassis of the rover. So really, you can think the body of this rover is Canadian. It's going to be driving around in 2020. And also, the eyes of the rover are Canadian. A company called NetTech has developed the hazard cameras and the navigation cameras. So really, this is another way that we're trying to implant the Maple Leaf on Mars through our industrial partnerships. Now, it's not just industry and it's not just hardware that we're contributing to missions like this, it's also expertise and knowledge. And so in certain cases, what we've been trying to do is to support Canadian scientists to participate on the science teams of various international missions. And so we're very happy to have been able to support a variety of scientists around the country on missions such as the Mars Science Laboratory, in addition to our AVXS contribution. We also have a scientist on the InSight mission, which will be launching next year, which will be examining the interior structure of Mars, and also on the ExoMars Trace Gas Orbiter. So really, we've got hardware elements, we've got expertise, we've got industry, and it's really a Canadian push to study Mars. Now, every time we build an instrument, we gain expertise and knowledge, and it gets a little bit easier each time, thankfully. So as was introduced at the very beginning, our most current instrument in flight right now is called the OSIRIS-REx Laser Altimeter, or OLA. This is a LiDAR that's actually based on the heritage of the Phoenix Mars Lander atmospheric LiDAR. We've changed around some of the components, but what this is going to do is actually measure, you can think of it as a 3D scanner that's going to go to an asteroid and build up a 3D shape model of the asteroid. So this mission is designed to retrieve a sample of a pristine carbonaceous asteroid and bring it back to Earth in 2023. So you can think of it as going out, it's almost a cosmic time capsule that we're going to grab a piece of the early solar system and bring it back to Earth to study in labs here. What's great is that of the sample that gets returned, Canada is going to own 4% of it. So we're setting the stage here for generations of science to take place. This isn't just the science we're doing on this mission in particular. These are samples that we're going to own and be in control of and control access to for our scientists for years and years to come. So I'm incredibly excited about this. Now, moving forward, there's obviously the robotic elements of space exploration and planetary exploration, but there's also the human element too. And one of the trends that we're seeing recently is that the overlap between robotic scientific missions and science enabled by human missions is really starting to pick up. And so in terms of the overall international planning for what's happening next, it's actually coordinated through something called the International Space Exploration Coordination Group, or ISG. And I guess this is a good time to mention to all the students in the room, if you're going to stay in space, start learning acronyms now, because it's not going to stop. So ISG, this is the international coordination body that's really setting the steps for how humans are going to explore the solar system next. The current plan was published a few years ago in what's known as the Global Exploration Roadmap, or GER. We're currently drafting the third iteration of this, which we're hoping will be released next year. And ultimately what this does is summarize the global plan for how humans are going to explore space. Now the current plan, as you may have heard in the news recently, is to think about what's going to be happening after the International Space Station is done. The agreements have only been renewed until 2024, but after that, it's time to start planning for that now. And so the current state of thinking is to develop a station and to put it into cislunar orbit. So it's a highly elliptical orbit around the moon. And so this is sort of the next step. Ultimately, Mars is the end destination for human exploration. But in order, we can't just go straight to Mars. We need to sort of take steps along the way. And so by pushing out deeper into space, it'll be able to test our capabilities, test our technologies, and frankly, test our human physiology as well, a lot tougher than we have been doing on the ISS. So you can think of it as that next step. What's great, though, especially from a scientific point of view, and obviously I'm biased, from a planetary science point of view, is that if we have a station in orbit around the moon, this will facilitate some fantastic science on the moon as well. And so right now, Canada is involved in a number of studies, in concept studies, designing rovers that could potentially go down to the moon to do various studies, both human-rated and precursor rovers that are just robotic, no humans involved at all. We're also involved in an extensive science maturation study, so really trying to look at, if we have a certain type of rover and we're at a certain landing spot, what are the samples we should be looking at? What can we potentially collect and return to Earth? So really it's this concept of going out and grabbing a sample of the moon and bringing it back to Earth is going to revolutionize our understanding. And that's the great thing about sample return, is that we can fly lots of cool instruments and we can fly spacecraft, but they have to be really light and take up almost no power. You're never going to be able to replicate the science on a spacecraft that you can do in terrestrial labs. And this is one of the driving factors. Oh, sorry, skipping ahead. So basically, I'll just skip that. We're testing some technology and lunar stuff as well. I want to get to the sample return because this is a particularly important point. From a scientific point of view, this is really, internationally, has been one of the quote-unquote holy grails for the last number of years. Bringing a sample home from Mars is the dream of planetary geologists throughout the world. People have been working on it for 20 years, 30 years, trying to figure out a way that we can go to Mars and bring these samples back. Because again, anything that we can study in situ will be dwarfed by what we can do with the sample and studying it on labs on Earth. And so the current architecture right now, it's challenging, it's tough. It's going to take at least 3 flight missions to do. The first would be a rover that would go out and select the samples and collect them and cache them. A second would be a lander with a roving element to go pick those samples up and to put them in Mars orbit. And then a third to go and catch the canister in Mars orbit and bring it back to Earth for return. So technically, it's a tremendous challenge. But what's particularly exciting is that some tangible steps are being taken forward. So the Mars 2020 rover, for example, from NASA, will be this first roving element. It is designed to select samples and cache them in a returnable fashion, such that future missions could potentially go and pick them up and bring them home. The thing is, doing this is tough. It needs a lot of practice, and one of the things Canada's been able to do, we have a particular strength in sort of these dress rehearsal missions. And so one of the things we've done over the last couple of years is outfitted one of our prototype rovers and taken it to an environment very similar geologically to Mars, to what you'd expect to a place that we're going on Mars to practice. And so without going into too much, I mean, I could talk a full hour about just this, but it was an amazing, it's full 4 weeks of operations where we drove around, we had a remote science team as we would with a planetary mission, commanding a rover in Utah, going around, sniffing the rocks, similar instruments to what you'd find on a flight mission, and doing sample collection. So really starting to refine some of these operational questions that we have about how to do sample return. Similarly, there's huge challenges once you've collected the samples and placed them in a returnable fashion, which is code for on the ground. What we need is technology that's able to successfully retrieve those samples and bring them back. And so what we did is we re-outfitted the rover with various, we took the science instruments off the end of the arm and instead we developed some technology for grasping and retrieving the samples. And I hope this works. So this is just a quick summary of what the retrieval mission looked like. And so this is obviously sped up a bit, but we egressed off of the lander, drove up to a sample, deployed the arm and the end effector to grip it, successfully selected and captured the sample, brought it back to the rover. What's interesting here is there's actually a lot of requirements on how and where you can touch the sample canister, and so trying to refine those with the technology in order to touch it in the right place and still collect it safely has been a tremendous challenge. But I give full credit to our engineers who did a marvelous job. So you can see then again the rover egressing. There's our rover control room back at the agency. 5 minutes. Okay, we're still doing okay. So again, the rover will come back through our autonomous software, and that's the thing. So this is all programmed ahead of time. This is a robot that's simply executing commands. This isn't being driven by a joystick. This isn't real-time anything, because on Mars you don't have that luxury, obviously. So we've been developing some of the software and some of the hardware that will allow these future missions then to go and retrieve the samples, hopefully cached by 2020, and return them safely to an ascent vehicle. So that was sort of the future look. I mean, certainly sample return, the Mars sample return in particular, has been a dream of the planetary science community for years. But really what we need to do as a country is listen to our community specifically and understand what its goals and its priorities are as well, because at the end of the day, we're here to serve the academic and industrial communities. And so periodically what we've done is gone out and solicited input from the community and brought them together and tried to really collate and understand what Canadian priorities are. So the most recently that we did this was just last fall, just down the road actually, where we spent 2 days really bringing together the full Canadian community and understanding where we should be going next, sort of 2025 and beyond. And in terms of the science, it's really been broken down into the four fundamental science disciplines. So astrobiology, is there life elsewhere in the solar system? Planetary atmospheres, speaks for itself. Geology, geophysics, and prospecting. And the planetary space environment actually emerged as well as an interesting topic. So this is sort of the region just outside of our planet where space weather can play a role. In terms of the aims of the report, so hopefully this will be a public document shortly. We're just working on some final revisions now, but the aim is to release it certainly so it'll be widely available for everyone to read. But really what we've tried to do here is to prioritize the investigations of what we're doing. And really, again, because we can't do everything, we'd love to do everything, but we can't. And so the question is, what are some of the most important investigations that we can carry out, again, in this 2025 and beyond neighborhood? So wrapping it all up then, you know, Canada really is an active participant in international planetary science. We've been to Mars, we're on our way to an asteroid, we're planning on supporting future missions to the moon. So it's really a dynamic environment. We've done our best to be a part of as many missions as we can. We've renewed the scientific priorities, so we're trying to keep current, we're trying to keep present, and we're really trying to listen to our community in terms of where Canada should be going as a space nation. And finally, obviously we can't do this alone, and no one can do this alone. This is what we're understanding internationally, is that agencies need to work together, and we really need to pull together in order to pull some of these things off. So it's really a challenge. Now, those are the very practical and programmatic take-home messages. But to me, this is the real take-home message of planetary exploration. So this, as was introduced earlier, is a picture of you and me and everyone in this building and everyone we have ever known. This was taken by a spacecraft that launched in 2016, went all the way around the sun, flew under Antarctica, flung itself out at a 6-degree inclination to go chase an asteroid. And this is an image that was taken by that spacecraft 1.2 million kilometers away from the Earth. This is the last time that this particular spacecraft is going to see the Earth until 2023, at which point it will be bringing back 60 grams to 2 kilograms of the early solar system. This is the reason I show up to work in the morning. And this, or something very similar to this, I would imagine, is why you're all here at this conference. And so what I'd hope for you, and obviously I wish you an excellent 2 days, but what I hope for you, and especially the students in the room, is take some time to meet the person next to you, and the person behind you, and the person across the aisle from you, because these are going to be your colleagues moving forward in this industry, and these are going to be your samples to work on when we bring them back. So take the time, meet people, go to some talks, learn something new, and more importantly, have fun, because at the end of the day, space is awesome. So